Yeah, hello, good evening, everyone. Yeah, hello, good evening, everyone. So, this is week 3 discussion for the course Solar Photovoltaics Fundamental Technology and Applications, which is being taken by Professor Soumitra from IIT Roorkee. And I am Ravi Kumar, a PhD research scholar under PMRF scheme at IIT Bombay. Okay, so let's start. So, first we will recap all the lectures. Like, let's make this a story how we started with the types of material and now we are at the solar cell. So how a material is being transferred into a solar cell. So what happens, we started with the different type of materials. What are those? Anyone can write in the chat box. Types of materials we have: conductor, semiconductors, and then insulators. Yes, Chaitanya, conductors, semiconductors, and insulators. Then in in semiconductors, we have P-type semiconductors and N-type semiconductors. It's like we are doping here. Then P and N-type become a PN junction. And this PN junction with metal contacts, anti-reflective coating, work as a solar cell. Any doubt here? Okay. So we are at the semiconductor. So we are at the solar cell. So now we will see, we have seen the IV characteristic of solar cell. We have seen some important performance parameters like VOC, ISC, VMPP, and IMPP. So these are some performance parameter, and like including 4 we have a fill factor. Yes, it is fine. Then we will move like add. So we will just see the IV characteristic of solar cell once again. So this is the IV characteristics. Here we have 3 points like VOC, the point at which current flowing through the load is 0, and voltage at the terminal is maximum. So it is known as open circuit voltage. Then we have ISC. If we have connected a load with a solar cell and the current flowing through the load is maximum, then the voltage across the load will be 0 and current will be maximum, and that current is known as short circuit current. And third parameter we have Pmax. So in this Pmax we have Imax, or sometimes we say IMPP. MPP means maximum power point. So it is maximum power point. So it is a point on the IV curve at which we can extract the maximum power from a solar cell. And corresponding to this point, we have IMPP. It is the maximum current at Pmax point, and this is Vmax. It is the maximum voltage at Pmax point. Imax is not the maximum current. It is the current flowing at the maximum power point. Vmax is not the maximum voltage. It is a voltage at maximum power point. So the maximum voltage of a solar cell can be equals to VOC, and maximum current can be equal to ISC. Any doubt here? Okay, so let's move ahead. Yeah, here only we have fill factor. It is fill factor. It is defined as equals to this area means this area divided by this total area. So this is like this area will be IMPP into VMPP, and this above area will be maximum, like bigger rectangle area will be, or square area will be VOC into ISC. So this is an important term, because sometimes what happen, this power point will drop, but our ISC and VOC will remain constant. Even the ISC and VOC of a solar cell are same, but we are not able to extract the required power or the maximum power from the solar cell. So there might be some kind of defects or degradation in the solar cell. We will see what are those defects and degradation and why this maximum power point drops. Okay, so let's move forward. Now we will see, we have seen, like we have just touched this topic. It is the electrical modeling of a solar cell. So solar cell is already an like we have PN junction. It is the material kind of thing, but same thing we can represent into the an electrical model with the symbols. So there, like ideally PN junction. So what is solar cell? Solar cell ideally is just a diode which is generating some current. Therefore, ideally, we represent a solar cell with a diode and a current source. This is the ideal solar cell model. So this is the PN junction diode, and this is an external current source. It is actually, there is no current source in a solar cell, but we are representing a current source here because the solar cell is doing what? It is converting photon into electrons, and that behavior is working as a current source. So ideally, we represent a solar cell with a combination of diode and current source. Any doubt here? Yes. So I am saying this is ideal solar cell, but in this universe nothing is ideal. There are many phenomena which occur in practical solar cell. So we need to consider all those phenomena in this solar cell modeling. What are those? Can anyone say? Do you know about it? You can just write in the chat box or you can speak whatever you want. If you have gone through all the lectures till week 3, then you must know this. Yes, resistance. There is actually no resistance, but this resistance is coming due to some other effect. So we represent in the electrical model with the resistance. Yes, Sindhu, you are right, it is resistance. So I'll show you the practical solar cell. So this is a practical solar cell, and this one was the ideal. This part is ideal, but we have this part which is external. It means this thing we already have inbuilt, but this is coming out of effect. There is no resistance. Actually, there is no resistance in a solar cell, but these resistance are coming due to some phenomena, which you will tell me right now. What are the sources of RS? First, I'll tell you what is this RS. RS is series resistance, and this RSH is shunt resistance. What is the meaning of shunt? Does anyone know this? What is the mean? You understood the series. It means it is having a series connection, one after another. But what is the meaning of shunt? Am I audible? It's like I'm not audible to you.
Yes, sir, you are audible.
Okay, okay. Thank you for confirming. Do you know the meaning of shunt? Parallel. Actually, the shunt meaning is not parallel. Okay, I'll tell you one thing. Just let me know the answer. What will happen if this RSH will be 0? The condition of solar cell if RSH is 0. Tell me the operating point of solar cell. Just I'll show you one thing. Let's see. This is an IV curve. I'm telling you if RSH is 0. So where in this IV curve, at which point my solar cell will work? It will work at which point? Just see once again. This is the model, and I am saying if RSH equals to 0, then what will happen? It is very simple. What are the, just think it this way. I am just putting RSH here. And if I am making this RS equals to 0, then what will happen? RS at 0 means I am connecting these two terminals. And if I am connecting these two terminals, I am short circuiting the solar cell. So that will be the short circuit condition. So that condition will be a short circuit condition. So shunt really means short circuit, which is taking towards the short circuit condition. That is the meaning of shunt. So that's why it is a shunt resistance and that is a series resistance. Now tell me the sources. I'll write here and you just write in the chat box. Series shunt. What is the source of series resistance? Okay, you need some more explanation. I'll tell you one thing. Let's consider this is a solar cell. We having like fingers. Do you know fingers? Bus bars. And we are having bus bars. Just see here carefully. So it's like we have solar cell, we have bus bars, we have fingers. These are nothing else means to collect charge carriers. So if there is any electron hole pair is generating here, it will go to the nearest finger. Then this will go to the bus bar. And then from the bus bar it will be going to the load resistance. Load resistance, we can say load resistance. So it will go to the load. So at what point this electron will be experiencing some kind of resistance? First, here only. First, we can say there will be some resistance on the sheet. That is the surface of the solar cell. So first is sheet resistance. Second, it is coming to the finger. So finger resistance. Then it will go to the bus bar. So third is bus bar resistance. Then there are some interconnect like one another after we have other cell and these are the bus bar connecting here. So these are soldered. Soldering is here. So fourth one is resistance due to soldering. And resistance due to soldering. So these are the things. Just think one point from where is electron is started its journey and it is following what path? So along the path, all the point at which this resistance is experiencing some kind of resistance, that all will be the sources of series resistance. So these all four, even more, plus anything else, will contribute towards this series resistance. Let me know any doubt here. There is no resistance in a solar cell, but due to other parameters or other phenomena, the electron experiences some kind of resistance, and those are the sources of series resistance. Just have a look on it and let me know if you have any doubt. Is it clear? Yes or no? If yes, let me know. If no, let me know. That series resistance depends on internal cell parameters. What internal cell parameters? Even RS is itself, no. Like doping of unit cell, no. It depends on the like seat resistance. If seat resistance is depending on the doping, then it will be, otherwise it will not. And if we say the parameter of a solar cell, then series resistance itself is a parameter of solar cell. All the things included in the electrical model are known as parameter of solar cell. And like I just told you, BMPP, IMPP, VOC, ISC, those are the performance parameters. And other than those, we have, like, this is understood, right? Yeah. Other than those performance parameter, we have the parameter of this diode, that is current saturation, saturation current, and ideality factor. Sorry, this resistance. This is the IPH, generated current. And we have the shunt resistance and series resistance. So for a single diode, I'll tell you, there are two models for a solar cell. One is single diode model, another is double diode model. So for simplicity, will stuck with the single diode model. And here we have how many parameters? Just let me know. How many parameters are there in single diode model of a solar cell? Just let me know the count. 8. Deepsika, what 8 you are telling me? Just can you write? Oh, are you including those ISC, VOC as well? Okay. Ideally, there are only 5 parameters for this single diode model and there are 7 parameters for double diode model. So here, what are the like parameter? First, I01, second, N1, third, RS, fourth, RSH, fifth, IL or IPH. These are the parameter of a solar cell. Whenever you see any paper or whenever you like come across anything which talk about the parameter of a cell, then those material, it can be a book, chapter or anything, those are focusing on these things. These are the parameters of solar cell. And why these parameters are important? Why we are talking about the parameter of solar cell? Just think a bit and let me know why we are talking about the parameter of a solar cell. What is the importance of these parameters? Okay, I'll tell you. It's like using these five parameters: I01, N1, RSH, RS, and IPH. We can generate the IV characteristics. And using this IV characteristics, we can get performance parameters. What are those? IMPP, VMPP, VOC, ISC. And from this we can get fill factor, and then we can get efficiency. So it's like different technology will have different parameters, and based on the parameter we can find out the efficiency of the solar cell. We can get the IV characteristics, and IV characteristics can tell each and every detail about the solar cell. So that's why these are important. Okay, now see, this is the most basic question. We are having diode, we are having current source, we are having resistance, we are having shunt resistance. But what is the meaning of those in reality? I just told you about the RS. But other than RS, there are other parameters as well. So we will see the meaning of those components as well. See, this is the solar cell, and you can see this is our PN junction. I'm drawing here only. Let's see. I'm drawing here only. It's like we have a PN junction, and this is one output. This is another output. But we are having current. But current source where it is situated in a solar cell, this itself is a current source. I'm just drawing a little bit. It is the entire solar cell. So this current source is also parallel to this PN junction. So this is our current source that we represent with the IPH or IL. This is our diode, and then if this is the current electron is here, it will go to finger, it will go to bus bar, so then it will go collected here. So there are coming some series resistance. See one situation here, listen carefully. Let's say there is an external or extra path here. Our PN junction is having some kind of impurity or some kind of defects. So there is an extra path here. So what will happen? The current generated here will go to this path and this will sink again here like this. So our electron which need to go to the outer circuit, which will be sinking inside the solar cell itself, and it will recombine with the hole here. It's like electron and hole. They will recombine. And this is the source of shunt resistance. That's why we are having parallelly one resistance that is known as shunt resistance. Everything is clear here? Yes, no? It is very important to know the phenomena which is giving rise to different parameters. Because if visually you know what parameter is representing what part of a solar cell, then your understanding will be at like another level. It's like you know each and everything from a electrical model only. But if there is some kind of change in electrical model, let's say RS is increasing. So what will you just imagine? There is more resistance to the electron. So there are some difficulty for the electron to flow on the surface of solar cell. If RSH is decreasing, I'll tell you one thing. The series resistance, okay, you just tell me, what are the ideal value of RS and RSH should be? Just write in the chat box. Okay, there are two options, infinite or zero, right? RS, Hindu is saying RS 0. Yes, definitely true. Okay, now let's see. You are saying RS should be 0. And one condition is right here, like RSH is become 1000 ohm. So what will you imagine? You just need to imagine what is happening on the surface of solar cell. So there are some finger breakage, some bus bar breakage. The path is not smooth for an electron to flow. So by just seeing one parameter, you can look into the physical phenomena occurring on the surface of a solar cell. Second thing, let's say RSH. Hindu said RSH should be infinite. Let's say RSH become 0. So what it will represent? It will represent there is no more a PN junction. It is a short circuited path. So there are some metallic impurity which are making this path completely conductive. So no current will flow through this outside circuit. All current that will be generated from other part of solar cell will be sink inside the solar cell itself. I hope it is clear. Okay. So this is the like PN junction diagram only. So what I am saying, I can draw here as well. Like this is our resistance, and here these are the current generation. So this is our current generation source, our diode. Short circuit path will be here, so RSH, and metal will be here, so one resistance we can represent here RS, and these will be the output circuit. Fine, and this is our single diode mode. Okay, how many of you know about this pveducation.org? If you have any doubt here, you can ask. I'm asking another question. How many of you know about this pveducation.org platform? I know, okay. Okay, we will go to this platform today only. We will see some effect or impact of these different parameters. Okay, so next thing is impact of series and shunt resistance. I told you from both things we can get physical picture of solar cell. And if we just take an IV curve, let's say this one, this is the impact of series resistance and this is the shunt resistance. If we see these kind of phenomena from the IV curve, we can tell it is the impact of RS and it is due to some finger breakage, cracks, or many things which are the sources of series resistance. And here, if phenomena is this like this on the IV curve, then we will see this is due to short circuit inside the solar cell. So this slide is only to know the impact of RS and RSH. At which part of IV curve the impact of this RS and RSH can be seen. Okay, now I'll go to this platform. Wait. I hope it is visible. We will go to this. Yes. I just open your chat so that if you ask anything, I can see. Okay. So this is a platform pveducation.org and it is having all the information about this photovoltaic technology. So I'm just jumping directly to this solar cell operation. We will see some interesting animations. So this is our solar cell. See, this is a solar cell without any light. If I click on this, some light is coming. If some light is coming, there is an electron hole pair generation. And this electron hole pair, like its electron is going from the outer circuit, and this is the hole, and it will go toward this rear side and it will recombine with the electron. So this is the working of a solar cell. So I was telling you about solar cell parameters, and this is an interesting way to see the IV curve of a solar cell. See, this is a diode only, and this is the diode diode equation. What will happen? We just click on this. So it is the IV characteristic of a single diode. Now we will click, then there will be some illumination of light. So it's like there is some illumination of light, and this is there are some current generated. So this is the light generated current. So this curve is being shifted downwards. I'll click once again. The intensity of this light will increase, and this will go down further. And for the simplicity, we just reverse it. So this is the IV characteristics of a solar cell. What the things I want to tell you. This website is having all kind of information you need. Okay, see, this is the fill factor. Fill factor means I just told you it is a like IMPP into VMPP divided by ISC and VOC. For simplicity, we can say it is the ratio of area of A divided by area of B. It is like cell with high impact factor, it is cell with low impact factor. You can see one thing, VOC and ISC are not changing at all. But this our maximum power point is changing only, and due to this change, fill factor is changing. So if you don't know this VMPP or IMPP point, so it is very difficult to tell about the efficiency or fill factor of a solar cell, or we can say the condition of a solar cell, because this fill factor is very important to know about the condition of solar cell. Okay, yeah, resistive effect I'll show you. See, this is the series resistance and this one is the shunt resistance. Now we will see what is the impact of this series resistance and shunt resistance. So let's say this is a solar cell. It is not having any kind of shunt resistance, but it is having only a series resistance. And if we just like, what is the ideal value of series resistance? 0. So it is the ideal value of series resistance. So here there are different curves. This green one is power, blue one is like cell with RS. It is the IV curve with RS, and this red one is the ideal solar cell, means without any resistance. So here x-axis and y-axis is the voltage and y is the current density. Or if we have area of a solar cell, then we can say current. So if I am increasing this RS, see which part is changing. So it is the this slope is changing. It is going this way. So this is the impact of this series resistance. And due to this maximum power point is also changing. And if maximum power point is changing, then the efficiency of a solar cell is decreasing. Same way, we will see the impact of shunt resistance. This is the shunt resistance. This is a solar cell with only shunt resistance. There is no series resistance. So see, ideally, the value of a shunt resistance should be infinite. So it is matching with the ideal cell. But as this series resistance, shunt resistance value decreases, what will happen? This part First, in case of series resistance, this lower part or near to VOC part was changing, but in this case, this part near to this ISC part is changing. See, this is the impact of shunt resistance. Okay, so based on this, just I'll ask you, and then we have impact of both. We can change here both. This is series resistance and this is shunt resistance with this. So we can change here both. Okay, it was all about this. So this was all about this pveducation.org. Now you can go to this link and all the things will be visible to you. So it's very interesting to see the animation and it is helpful in understanding the effect of different parameters. Okay. So next is the manufacturing of crystalline silicon. So does anyone know the process of obtaining crystalline silicon? Okay, which element occurrence is the highest in this universe or Earth? We can say Earth.
Oxygen.
Oxygen. And after oxygen?
Silicon.
Yes. So means there is abundance availability of silicon. But that is impure silicon and we need pure silicon. So it is very like energy intensive and costly process to get the purest form of silicon. There is an interesting video I'll show you. My screen is visible? Yes, it's visible. I can see. Okay. So I'll just show you some video or some part of this video. So we are going to see how a monocrystalline and multicrystalline are obtained. So first we have this like rock form, then we get it metallurgical silicon. How? So they are like rock form. It is being heated. So after heating, it becomes some in molten state and some impurities are removed. So now we have metallurgical silicon, and from this metallurgical silicon, we need to obtain polycrystalline silicon. So how we will go it? So see, this is like Mg silicon and this is HCl, and then it is removing silicon with the HCl there. So it is making its more pure form. These equations are already given in the lectures. You can see those equations and understand. So now this is silicon HCl3, a complex structure, 3 Cl bond and 1 hydrogen with the silicon. Okay, anyone can tell me the name of this process? Name of this process? Siemens. Yes, yes, Vinod, you are right. Siemens. So during this Siemens process, we will get polycrystalline form of silicon. It is still having some impurity. So we have removed silicon, chlorine and hydrogen here. So now from polycrystalline, we need to obtain monocrystalline silicon, or that is in the form of silicon ingot. So it's like all the liquid form of silicon, and we are having one silicon, or we can say small amount of crystalline silicon, and we are dipping it into the molten state of silicon. So it's like they are having different orientations, and the one which we dipped in this molten state having one ordered silicons, all the atoms in a orderly pair. So what happens, those will be attracted in the same order, so that will convert it into a single crystalline form. As you can see, these are the silicon atoms and they are going into the same order. Now you can see we are getting an ingot. What is the name of this process? Anyone can tell? It is Czochralski process. Now we have got like from this polysilicon to monocrystalline silicon. Now we need wafers. This is making it is more pure. Heating and cooling again and again. Float zone process. Okay. So now we got this ingots and multicrystalline ingots. Now we need to convert it into wafers. For the multicrystalline, we don't need a single crystal or singly ordered crystal or singly ordered silicons atom. So what we just heat the different leftover from these processes having high purity. It's not like impure silicon, it is also pure silicon, but the order of atoms is not same on the entire wafer or on the entire silicon slab. So here just we are just heating it and then cooling it. So then we got this multicrystalline ingot and monocrystalline ingot. And from these ingots we get wafers. So these are some wire cutting techniques. So those wires are cutting and then we are getting the wafer. Then they are making those wafers more smooth. It is other form of like making. So here you can see from this rock form to metallurgical silicon, from this to polycrystalline silicon, and from this an ingots and from this vapor. So this is the entire process. Okay. So we have seen different processes as well as PV education portal. So now it's time to do some questions. So first question says, in the process of Czochralski method, which of the following relation is appropriate between melt and growing crystal? And these are the options. A, B, C, or D. A is saying melt and growing crystal are usually, it is saying not related to each other. It is saying rotated counterclockwise. It is saying rotated clockwise. It is saying at a constant position. So can you tell me what was the condition? Were they rotating counterclockwise means in opposite direction to each other or in the same direction, or they were constant or they were not related to each other? Just tell me A, B, C or D. same direction. Okay. C, counterclockwise. Yes, Sindhu, you are right. Deepsika, they were rotating in the opposite direction. So the correct answer is C. Oh, sorry, it's B. Counterclock direction. Yes. Not wrong. It's right. Yes, Sindhu, you are right. No, Sindhu, you are not. It's saying counterclockwise. I am saying if it is our single crystal silicon and this is our crucible having molten state of silicon, if it is rotating this direction, it should rotate in opposite direction. So it is counter. So correct answer is here is B, counterclockwise direction. Here you can see it is rotating in this direction and this one is rotating in this direction. So these direction are opposite. They are counterclockwise. Next question says you need to solve this question. It is very simple. It is saying 1 centimeter square silicon solar cell has maximum power PM equals to 12.96 milliwatt and is illuminated with sunlight yielding a short circuit photocurrent of 25 milliampere. Calculate the solar cell efficiency and fill factor if VOC is given. These are the options. It is very simple. Just need to put two different formulas and those are the simplest one. If you are not doing it, just let me know. I'll solve it for you. And if you are trying, then please try it. A. Yes, Deepsika, it's A. A is the correct answer. So those who are not solving it, I'll tell you. First, you can calculate fill factor. It is like this: VMP into IMP divided by VOC into ISC. And this VMP IMP is PM divided by VOC into ISC and equals to 12.96 into 10 to the minus 9 watt divided by 0.620 into 25 into 10 to the minus 3 ampere. And if you will solve it, you will get around 83%. And for the efficiency, it's like eta equals to power output divided by power input. So power output is 12.96 into 10 to the minus 3 watt divided by 100 milliwatt per centimeter square into 1 centimeter square into 10 to the minus 3 to convert it into watt. And then you will calculate, it will come around 12.96, which is equals to 13%. So this is the A is the correct answer here. Now let's move to the next question, which says a 40.46 micrometer thick sample of gallium arsenide is illuminated with monochromatic light of H nu having 2 electron volt. The absorption coefficient alpha is 5 into the power. Yes, it is saying, oh, these are the options. It is saying the absorption coefficient is 5 into 10 power 4 per centimeter square. The power incident on the sample is 10 milliwatt. Find out the total absorbed by the sample per second. Joule per second means what? For this, you just need one formula. It is for the transmitted power. We can calculate it like this. Transmitted power equals to P naught incident power into exponential of alpha into L. Alpha is given here and L is given here, thickness. So using this, we can calculate PT, and we know P incident equals to P absorbed plus P transmitted. So P absorbed will be P in minus PT, and P in is equal to 10 milliwatt minus PT. So you just need to calculate this PT. Are you solving it? Please solve, calculate this PT using this formula. P naught is the incident one. Solve it and let me know. Solve it. Just get this PT and then just get it subtracted from 10 milliwatt. D. How D can be? Let me solve. It's like exponential minus 5 into 10 4 centimeter into 0.46 into 10 minus 6 meter. So this is the solution for D. I think Deepsika it should C. See, this is the solution. This is PT, P naught, and we just put values here. Okay, okay. So you got it 9, right? Okay. So if you will solve it, you will get 1 milliwatt. And if we just subtract, okay. Okay, then it's fine. So from 10 milliwatt, we will subtract 1 milliwatt, then we will get 9 milliwatt. Yes, C is the answer. Let's move forward. So for ideal solar series resistance RS and parallel resistance RP should be what these are the options. It should be RS and RS. Very simple. A RS should be infinite. Yes. B RS should be 0 and RSH should be infinite. Yes, Sindhu and Deepsika, you both are right. It's B 0 and infinite. B is the right answer. Let's move forward. The value of solar constant is, these are the options. This question is repeated from the first slide, first week. Value of solar constant. A, B, C or D? It's C. Nobody knows. Okay. I'm telling you it's C. C is correct answer. So the value, solar constant value is 1366 watt per meter square on the surface of Earth. 31,366 or 67 watt per meter square. Fill factor is defined as, this is the definition of fill factor, A, B, C or D. Even we have solved the question, so you must know this. C. Deepsika saying C. Yes, C is the correct answer. 3 can't be here, 2 can't be, 3 here can't be. So it is C. Next question it says, a solar cell under illumination of 600 watt per meter square has a short circuit current 16.1 milliampere. It is saying at this illumination it is having this short circuit current and this open circuit voltage. What are the short circuit current and open circuit voltage when light intensity is doubled? See, these are the options. So we can say condition 1, condition 2, and this is our insolation. This is our ISC. This is our VOC. VOC was 0.485. ISC was 16.1 milliampere. This is volt at 600 watt per meter square. It is saying at 1200 watt per meter square, what will be the ISC and what will be the VOC. So you need to find out the question mark. If you need any formula, let me know. I'll give you a formula. Even without formula, you can solve this question. If you need formula, let me know. Okay, just tell me about current. If it is 16.1 milliampere at 600 watt per meter square, then what will be the current at 1200 watt per meter square? For the current, we don't need any kind of formula. We need a formula only for VOC calculation. Yes, is it? Yes, both are right. Deepsika, you are also right. And Sindhu, you are also right. Is it 32.2 milliampere? See, what is insolation? It is having number of charge carriers. If insolation is increasing, means number of charge carriers is increasing. If two photon were given two electron, then four photon will give four electron. So it is a direct relation. So current will be double. But in case of a VOC, it is not a direct relation, it is logarithmic relation. And this is the formula here. So it is exponentially related with the VOC. So this is the equation for single diode for an ideal solar cell. And what will happen at VOC, I will be 0. So by putting this condition and ignoring this one because this is more greater than 1, we will get this equation. And we have given 2 VOC, 2 IPH condition. So by taking a difference, these two we will get this equation. And by putting the values here, yes, answer is B. By putting value here like VOC 2 will be equals to VOC1 is how much? 0.485 volt plus NKT by E, and it will be double. But just by solving it, you will get VOC will be 0.503 approx. So answer will be B. This is the VOC. Okay, let's go to the next question, which says for minimum reflection, the thickness of TCO layer should fulfill the following requirement, where D is the thickness of TCO and N is the refractive index of TCO. Without the equation, how can we say about voltage, sir? Voltage, we can say it will be there will be some change in voltage, but it is an exponentially related with the this insolation or intensity. So the change in voltage will be minimal. We can't say exactly how much it will be, but to get the exact value we need equation. But without an equation, we can say the change in VOC will be minimal because it is exponentially related with the intensity. Okay, so this question is about TCO. First, let me know the TCO, full form of TCO. What T stand for? Transparent conductive oxide. Yes. Where it is being used in solar cell? Which technology? Thin film technology. Okay, these are the options. A, B, C, or D. It is A. It is related to the reflection of light. Will it be transmitted or it will be reflected back? Because it is on the surface of a solar cell, so the thickness and refractive index of this TCO layer should fulfill this criteria so that the light incoming from the any source like sun should go to the solar cell by passing through this TCO layer because it is on the surface of a solar cell. TCO should not block any light incident on the surface of solar cell, and this is the criteria. Okay, so we done with the today lecture, and those were the questions. And I'll upload this video along with this PPT on the YouTube channel. So if you have any doubt, you can ask there as well. So I am done from my side. Okay, thank you everyone. We will meet next Friday. Thank you everyone. Okay, I'm ending this class. Have a nice day.